Okay. 49, uncharged capacitor is connected to a 21 volt battery until it is fully charged, after which it is disconnected from the battery. We don't know what the capacitance is, but if we did, we could find the Q. The total charge would be the capacitance times the voltage times 21 volts. Would be the total charge enclosed. Now, what will change when you slide in a slab of paraffin? And that's where you got that 2.2 he was telling you about. Okay. Well, once it's fully charged, you take away the battery, Q is still equal to C, its initial C naught times 21 volts. You slide in a sheet of paraffin. What changes in this equation? Well, voltage is going to change. Is Q going to change? How is Q going to change? No. So if you disconnect the battery, Q can't go anywhere. Whatever this one's charged to, the total Q on the capacitor is still there. Now, yeah, in time it will leak out. It'll leak across. But initially, the Q doesn't change. In an ideal capacitor, Q will not change. So, C naught times 21 volts is going to be equal to, what will the new capacitance be? Will be equal to this new capacitance. The C naught, the initial capacitance, whatever it was to begin with, times K is the new capacitance. Okay? And it will be times some voltage. Well, if you want to find out what that voltage is, you divide both sides of this equation by the new capacitance, Cp, which is K times the original C, and you end up with C naught times 21 volts divided by K times C naught is equal to your new voltage. The C naughts cancels because you don't care what the capacitance was, but the new voltage will be 21 volts divided by K, which is 2.2. Cyrus. Huh. Look at this. Everything I still have to hand back goes to Wade, and he's not. Oh, there you are. Boom. Make sure you sign the sign-in sheet. Has anyone else snuck in on me? Okay. What was the other question? $38 and $55. A 0.2 farad capacitor is desired. What area must the plates have if they are to be separated by 3.2 millimeter air gap? Okay, well, let's see. Where's our equation for capacitance? It's epsilon sub naught times area divided by distance, or gap. So, capacitance equals epsilon sub naught times area over D. Epsilon sub naught is 9 times 10 to the minus 12, or 8.8. Okay, close enough. And the depth, the distance, D, is going to be what? And we want 0.20 farads. Okay, all we got to do is solve for A. 3.2 times 10 to the minus 3 times 0.2 equals 8.8 times 10 to the minus 12 times A, and if we divide that by 8.8 times 10 to the minus 12, we get 72.3 times 10 to the what? So, 72.3 million square meters. How to do it algebraically? Yeah, well, what you do it is C equals epsilon sub naught times A over D. C is a given, so you multiply both sides by D. And then you divide both sides by epsilon sub naught. And you're left with D, C over epsilon sub naught equals A. Now, got your pictures took? Notes took? All right. What was the other one you wanted to look at? Okay. Homemade capacitor is assembled by placing two 9-inch pie pans 4 centimeters apart. So, we're going to the area of the disc is pi r squared. R would be 4.5 inches. What's pi times 4.5 inches squared? No, don't square it. Don't multiply by pi and then square it. You square 4.5 and then multiply that by pi. 63.6 square inches is our area. What's the D? putting them how far apart? Ah, now we got to go from, we either need to start over and change that to centimeters, or we can just change centimeters into inches. So we've got how far, how many centimeters? 4, 4.0 or 4? 4 centimeters times 1 inch per 2.54 centimeters. So 4 divided by 2.54 equals? Okay, we're going to call that 1.6 inches. You know what? Let's leave 1.57 since we got 3 digits here. We'll round it down to 1 significant digit when we get to a final answer. All right. So our capacitance is 8.8 times 10 to the minus 12 times 63.6 square inches divided by divided by 1.57 inches. And why is that not going to work?
Well, what I did,
You were doing the right thing, but look what happened here. We've got inches squared divided by inches. That means this ratio is not unitless. It has units of inches. Okay? This is not written, that constant is not in units of inches. It's in SI units, which means this needs to be in meters, kilograms, and seconds. So, now we adhere to the old rule that there's never enough time to do it right, but there's always enough time to do it over. The diameter of this plate is 9 inches. Times 2.54 centimeters per inch is how many centimeters across? 22.86 centimeters, which is 0.2286 meters. Because we need to be in units of kilograms, meters, and seconds. Now, that's the diameter. The radius is 0.1143 meters. And that gives us an area of pi times 0.1143 squared, which is what? .041 square meters. Now, we can calculate the capacitance as epsilon sub naught times A over D, which is 8.8 times 10 to the minus 12 Newton meters, squared coulombs, whatever, times 0.041043 meters squared divided by 4 centimeters is how many meters? What does that come out to? So 9.0 stuff times what? So to one significant digit, 9 picofarads is the capacitance of these two plates. Now it's connected to a 9-volt battery. What would the charge on each plate be? Capacitance times voltage. So if it's what, how many volts? 9 volts. So 9 picofarads times 9 volts. (81 times 10 to the minus 12 coulomb, or 81 picocoulombs. Is that what everyone else gets? All right. What is the electric field halfway between the plates? Yeah, it's going to be a uniform E field. Minus E times D. Yeah. The voltage across is minus E times D, so the voltage is what, 9 volts? And the distance was so 9 divided by 4 times 10 to the minus 2. Voltmeters or volts per meter? Okay. Yep, 225. Now, What was the work done to charge that? Say again? Well, it's, let's see, work is equal to charge times delta V. Now, what is the charge? Capacitance times voltage. And the delta V is simply the voltage across it. So 9 squared is 81. And C is what? 9 times 10 to the minus 12? Okay. Say it again. What half? You're talking about energy stored. That's not what was asked. Yeah, let's make sure we're answering the right question. The work done by the battery to charge the plates is not the same thing as the energy stored. I haven't done the arithmetic, so let's see, 9 times 10 to the minus 12 times 81. $7.29 times 10 to the minus 10. What does the book say? By golly, they did. Well, they got 200 volts per meter because they're only using one significant digit. We got what? 225 to one significant digit is how much? Now, where did they get? Because that is not what they asked. The work done by the battery to charge them. Yeah, well, Mama's wrong again. I think they did. I think they used the. Now here they say work equals Q times voltage divided by 2. Why do they divide by 2? Oh. No. We're on 55, but I see why. They're taking the average of the voltage. That's exactly why. So their book is not wrong. Your mama was wrong this time. It is. It is the average voltage. Because think about this. Think this through. The work that's being done is you're going from V final. So the closer you get to the V final, the more you're having to work. The voltage, in other words, the voltage is not uniform going across. The E field is. The voltage is not. So you have to talk about the work in terms of the average voltage. So it would be times the voltage average, which would be 9 divided by 2, which is 4.5. And Q is what? C times V. So that basically, well, yeah, here, instead of the average voltage is V over 2, and Q is C times V over 2 is C V squared divided by 2. And that would mean this would actually come out to be 3.645 times 10 to the minus 10 joules. But to one significant digit, 3.6 is 4. Yep. You got to be real careful before you decide the book was wrong, because it's been checked and rechecked many, many times. It's like I think I'm the only person in history who's ever been at fault when his check bounced. Everybody else, when their check bounces, it was the bank's fault. Did anyone have any questions about any of the other homework? Did everybody sign this? Anybody not signed in? And yeah, Wade was the last one. I've given back everybody's everything. So then let's start talking about electrical currents. Because so far all we've talked about is static electricity, which is interesting and fun, but not real useful. Unless you want to shock someone on the back of the ear with the shuffle your feet across a carpet. Today, it's take home. It would have been on Monday, but we had a holiday, so I don't want to fall behind another day. Yep. Pesky holidays running my schedule. Ooh, it's dark out here. Hoorah. Who can tell me what the modern what's the reference to the modern Prometheus? The modern Prometheus. And before you're taken too far aback by the word modern, I'll tell you the reference comes from a couple hundred years ago. Prometheus was the movie, the sequel to the prequel, whatever, to Alien. Yeah. But why did they call that ship Prometheus? Why did they call that movie Prometheus? The original Prometheus was a god or a demigod in Greek mythology, or maybe it was Roman mythology, I don't know, probably. But he got in trouble because he stole the secret of fire from the gods and gave it to man. And so the gods got angry with him and they punished him. The modern Prometheus, is a reference to what literary character? Devil's not a literary character. The modern Prometheus went down to Georgia and tried to play a fiddle of gold. I don't know how many of you have ever tried to play a fiddle, but trust me, if it was made out of gold, A, you couldn't lift it, and B, it would sound terrible. It sounds something like a cat stuck in a blender. Modern Prometheus is the subtitle of the book Frankenstein. No.
That's what I was thinking about, like God.
Mary Shelley was married to some poet back then. Percy Shelley? Maybe I'm thinking of Percy Sledge. I don't care. She was married to a poet, but she wrote the book Frankenstein about a fellow named Dr. Frankenstein who was pursuing what was the great pursuit at that time, was the secret of life. What was this mysterious life force that gave life to living creatures? And a lot of people at that time believed that this mysterious life force was what we now call electricity, electric force. No, actually, there was a. Have you ever heard of the galvanometer? Okay, a scientist back in the 1700s named Galvani. He had, in fact, he published his work where he had made frog legs, dead frog legs, dismembered frog legs. He made them twitch and jump, made the muscles contract by inserting dissimilar metals into the muscle tissue of the frog legs. And he was convinced that this electric force that he was playing with was this mysterious life force that all of the scientists were looking for, trying to discover and identify. Galvani thought that the source of the electricity in the frog leg twitching was the muscle tissue itself. And he, in fact, he called it in his publications, he called it the life force. But like, what was the guy's name? The professor in Waterboy. Colonel Sanders. Like Colonel Sanders, he was wrong. In fact, not, but, well, right then, during his lifetime, another scientist named Volta had, he did some other experiments, and what he figured out was that the muscle tissue was not the source of the electricity. It was just a convenient conductive material that the source that the electricity could flow through, and it reacted. What Volta figured out was that these frog legs were much more sensitive instruments for measuring and detecting small trace currents than even the most sensitive instruments he had been able to develop at the time. Volta published his work in 1800, and he discovered that the source of the force of the electricity was actually the dissimilar metals. It was the nature of dissimilar metals combining two different metals together. And that depending on which metals you used, they would produce either more or less electromotive force, what we now call voltage. And he published tables of relative potential differences, relative electromotive forces between different pairs of dissimilar metals, charts of which are still used today in chemistry. And if you're in instrumentation, you use them as well. How many of you are doing instrumentation work? How many of you have ever heard of a thermocouple? How does a thermocouple work? Nope. It's sensitive to heat. But it works by combining dissimilar metals. And when you get two dissimilar metals in contact with each other, even after you weld them into a nice, neat, pretty little ball, they will generate at the molecular level a potential difference from the one metal to the other. And the chemistry of what goes on in order for that to happen is beyond the scope of this course. We'll look at a simple case of a wet cell battery here in a bit. But turns out that potential difference that they make, tiny, tiny little bitty difference of potential, but it's very linear. It can be very linear, and it's very repeatable. And it is sensitive. It depends very much on the absolute temperature of the two dissimilar metals where they join together. And that's how thermocouples are made. How many of you, I don't guess y'all have, it's been since the 70s when this was a problem. But back in the 70s, a lot of contractors all around the country started using aluminum wire to build their houses, building houses, instead of copper wire, because copper got just stupid expensive. Aluminum was a lot cheaper, so they saved money, built houses with aluminum wiring, and it didn't take too many years before those houses started catching fire and burning down. No, that's not what was causing the problem. Causing the problem was all the receptacles and the light switches that they connected those aluminum wires to still had terminals that were made out of brass and copper. And by connecting the dissimilar metal between the aluminum and the brass or the copper on the terminal, it would produce a small potential difference. And that small potential difference would start producing an accelerated oxidation reduction reaction. It would corrode and build up a high impedance, a high resistivity at the connection, which would then start dropping higher and higher voltages and dissipating more and more power right there across that connection until it overheated enough and it caught fire. Everybody looking at their watch. Am I really running out of time already? Don't look at your watch. Oh. Oh, everybody, it's raining. Okay, back to class. The potential difference of that chemical, electrochemical reaction between dissimilar metals is what caused all those fires in the 70s, which is why they had to go in and rewire all those houses back to copper wire. Actually, they found ways to fix it, but that's another course. What Volta's greatest contribution was when he discovered that he could take and replace either of those dissimilar metals with just carbon and still generate a potential difference between carbon and those other metals. And that's the relative scale that he ended up developing that's still in use today. The different potentials from dissimilar metals. Anyway, he discovered that if he took that, replaced that one of those with carbon, and then created a cell, put another kind of metal across it with some kind of wet conductive medium between it. He used a lightly acidic substance. At any rate, he put an acid, a weak acid between the carbon and the other metal. Usually, I think he used zinc. Then that would produce a potential, and it would produce current. But he then discovered that if he stacked a bunch of these on top of each other, he literally piled them up into a battery, then he could increase the potential difference, seemingly without limit. The more cells he stacked on top of each other, the higher the voltage got. Higher and higher. He got the voltage so high that when he took two wires connected to both ends of the battery and brought them close enough together, he could produce a spark, an arc. What's the breakdown voltage of air? No, that's the coefficient of permittivity. That's the K, dielectric K. Permittivity of air. Breakdown voltage of air, the dielectric strength of air, is 3 million volts per meter. So he had to build up some fairly significant, a whole lot more than just, the few millivolts you would get from the 1 or 2 volts you might get from a simple cell. He built up enough voltage where he could create a spark, where he could break down the dielectric strength of air. And that was a huge step, because that's when he discovered that he could then connect that battery to a circuit and provide a steady and sustained flow of electricity, an electric current. So, let's get some terms. What is that the symbol of? No. But you're close. In point of fact, it probably nowadays is used as a symbol for a battery, but it is technically not a battery. This is the symbol for a single cell. That is the symbol for a battery. A battery is multiple cells connected in series to produce a greater voltage. Those AA's and AAA's that you call batteries, those little button batteries that go in your calculator, technically those are not batteries, those are cells. That's why they were called D-cell batteries or C-cell batteries. If you had a flashlight that needed D cells, it needed a D cell battery in order to power that flashlight. You'd have to put 2 or 3 D cells in as a battery to power. I don't know how many of you are old enough to remember, but when I was a kid, the battery in your car had 6 holes on the top with little screw caps that you had to open up and check to make sure there was still water in it. Yeah, that water was actually sulfuric acid. That's why when you replaced it, you had to use distilled water, because if you just used tap water, it would contaminate and it would kill the battery a lot faster. The battery would last longer if you used distilled water when you replenished it. Each one of those caps was 1 cell, and each cell produced 2 volts. So when you had 6 volts, 6 of those cells added together, you ended up with a 12-volt battery. D cells, AA's, AAA's, those are 1.5 volt cells. So you put 2 of those in series, you've got a 3-volt battery. Electric current. Symbol is I. Why do we use I for current? Because it was originally, the man who originally did the work was Andre, I think? Whatever. Ampere was his name. He's a Frenchman named Ampere. And he called this electric current intensity, which is the French word for intensity. It's amazing how often you can speak French if you just say it snooty enough. That's what the I stands for, intensity. And the amp, named for ampere, is the unit of electric current. It's actually current is actually change in charge, the electric charge, Q, or coulombs per second. So, if you have 1 coulomb of electricity, of electric charge, flowing past a point in a wire every second, 1 coulomb in 1 second, that is the definition of 1 amp of current. Actually, I think now they've changed the definition, so amp is now considered a fundamental definition. This is where it came from. However they define it today, this is still true. How many? We've already looked at this, but let's look at it again just in case. How many coulombs is 1 electron? Coulombs per electron. So how many electrons would have to flow past a point in the wire in 1 second in order to produce one current. There's 1.6022 times 10 to the minus 19 coulombs per electron. How many electrons are there in 1 coulomb? .24 times 10 to the 18, I think it is. 6.24, 6.25 times 10 to the power of 18 electrons. Per coulomb. Real quick, how many protons would it take to make 1 coulomb of electricity? The exact same number. Because they have the exact same charge as an electron. Now, one more thing I want to cover before we go, and that is current. What actually flows? Well, in a wire or any kind of conductor, you have electrons that are actually moving. It's all those free electrons in that metal lattice structure that are free to migrate from one atom to the next in the structure. And those electrons moving are what actually flows in electrical current that we normally think of. But 200 years ago, when they were making up all these definitions, out of random and arbitrary choice, they decided, well, it's positive charge that flows from the positive terminal to the negative terminal of the battery, or however they worked it out. So now we call positive flow conventional current. If we're talking about negative flow, we call it electron current. Which one is real depends on what you're talking about. If we're talking about electrons flowing in a conductor, in a wire, then it's actually electrons that move. The protons don't. They stay put. In that fluorescent tube, it's both. You have positive ions flowing in one direction and negative electrons or negative ions flowing in the other direction. So in a gas or in a liquid, it can be either. You can literally have positive ions are the mechanism of the electric current. So, we're just going to try and make sure we keep straight about what we're talking about. Generally, if we talk about current, it's going to be conventional current or positive flow. Now, in the case of a semiconductor, since we got 2 more minutes, which is real? Which is it that actually happens in a semiconductor? You've got your p-type doping and your n-type doping, your p-n junction. Is it the electrons that flow from negative to positive, or the holes that flow from positive to negative? Which is it? Yeah, that's what physics would suggest, but it turns out experimentally you can prove that it's actually the holes that move, that do the work. Because the holes carry the smoke. And if you let the smoke out, then it doesn't work anymore. And that just went right over everybody. Go home. Say, I'll see y'all on I'll see you tomorrow for lab. We're going to do the Wheatstone Bridge lab. You sure do. Here's the exam. Be sure to turn it in tomorrow in lab. Everybody make sure you've signed in. And get an exam before you leave. Bring them back to me for lab tomorrow. These were not intended to be take-home exams, so there's no excuse for anybody not to ace it. You get one? You got one, Deb? Yes. Who else needs one? See y'all tomorrow.